In this video, we are going to discuss the law of mass action. The effect of concentration on the rate of chemical reaction. It is explained on the basis of law of mass action. What is the statement of law of mass action? According to law of mass action, the rate of chemical reaction is directly proportional to product of active masses of reacting substances. What do you mean by active mass or active masses of reacting substances? It is nothing but molar concentrations of reacting substances, and hence the rate of chemical reaction, it is directly proportional to product of molar concentrations of reacting substances. Now consider the general reversible chemical reaction. A plus B reversibly gives C plus D. This law of mass action applicable to reversible chemical reaction. And here 1 mole of A reacts with 1 mole of B. There is a formation of 1 mole of C and 1 mole of D. According to law of mass action, rate of forward reaction depends upon molar concentrations of A and B, and therefore rate of forward reaction, it is directly proportional to molar concentration of A into molar concentration of B, and therefore rate of forward reaction, that is RF, it is equal to some proportionality constant Kf, that is velocity constant or rate constant, into molar concentration of A into concentration of B. Similarly, for reverse reaction, the rate of backward reaction or rate of reverse reaction, that is RB, it is directly proportional to molar concentrations of C and D, and therefore RB, it is equal to Kb. Kb is a velocity constant or rate constant for backward reaction into concentration of C into concentration of D. But at equilibrium, rate of forward reaction and rate of backward reaction is equal, and therefore these two equations becomes Kf into concentration of A into concentration of B, it is equal to Kb into concentration of C into concentration of D. By rearranging terms, we can write Kf upon Kb, it is equal to concentration of C into concentration of D by concentration of A concentration of B. This ratio of velocity constant or rate constant for forward and backward reaction, it is nothing but the equilibrium constant denoted by capital K, and therefore K is equal to, that is equilibrium constant, it is equal to concentration of C into D upon concentration of A into concentration of B, and this equilibrium constant K remains constant for a given temperature and pressure. Now consider another general reaction, that is A moles of A reacts with B moles of B to form C moles of C and D moles of D. For this reaction, equilibrium constant Kc, that is for liquid state reaction. In liquid we express the extent of reactant and product in terms of concentration, whereas if reaction is in gas phase, then extent of reactant and product, it is expressed in terms of partial pressures, and therefore Kc, that is the equilibrium constant for liquid state reaction, it is equal to concentration of C raised to C into concentration of D raised to D upon concentration of A raised to A into concentration of B raised to B, where small a, b, c, d, these are the coefficients A, B, C and D, and capital A, B, these are the reactants, capital C, D, these are the products. Now consider the gas phase reaction, that is A moles of A gas combines with B moles of B gas to form C moles of C gas plus D moles of D gas. And for gas phase reaction, or if reactants and products are in gaseous phase, then K is expressed in terms of partial pressures, and therefore Kp, that is equilibrium constant for gas phase reaction, it is equal to Pc raised to C, that is partial pressure of C raised to C, upon Pd raised to D, that is partial pressure of D raised to D, upon Pa raised to A, Pb raised to B, where Pa, Pb, Pc, Pd, these are the partial pressures of A, B, C, D respectively. So this is what is the law of mass action. Now next point is characteristics of equilibrium constant. Equilibrium constant K, it is expressed in terms of Kc or Kp, and it is independent of initial concentration of reacting substances. Another important character is rate increases with extent of K, or it depends upon the value of K. Greater the value of K, greater is the rate of forward reaction, or higher is the percentage of product formed. Now next important character is the units of Kc and Kp depends upon the stoichiometry of chemical reaction, that is number of moles of reactants and products, and the value of K, it is independent of presence or absence of catalyst. Okay, these are the characteristics of equilibrium constant. Now next important point is relation between Kc and Kp. Now let us consider general reaction. A moles of A plus B moles of B gives C moles of C plus D moles of D. And according to law of mass action, Kc is equal to C raised to C into D raised to D upon A raised to A, B raised to B. This is equation number 1. Now for gas phase reaction, Kp is equal to, we can write partial pressure of C raised to C into partial pressure of D raised to D upon partial pressure of A raised to A into partial pressure of B raised to B. This is equation number 2. But we know that PV is equal to nRT. This is for ideal gas. By rearranging terms, we can write P is equal to nRT by V, and this ratio, number of moles upon volume, it is nothing but the concentration, and therefore we can write P is equal to CRT, where C is a concentration, and concentration, it is equal to number of moles upon volume. So for gas or for any particular reaction, we can write P, it is equal to CRT, where P is a partial pressure, C is a concentration, R is a universal gas constant, T is absolute temperature. Then for reactants and products, we can write for reactant A, the partial pressure of A, it is equal to molar concentration of A into RT. For reactant B, we can write partial pressure of B equal to molar concentration of B into RT. Similarly, partial pressure of C equal to molar concentration of C into RT, and partial pressure of D, it is equal to molar concentration of D into RT. Now we know the values of partial pressures of A, B, C and D. Substituting the values of partial pressures in this equation number 2, we get Kp is equal to, now we know Pc is equal to, Pc is nothing but concentration of C into RT, and therefore concentration of C raised to C into RT raised to C, because here coefficient is C, and therefore concentration of C raised to C into concentration of RT raised to C. Actually here it should be not concentration of RT but RT raised to C into concentration of D raised to D into RT raised to D upon concentration of A raised to A into RT raised to A into concentration of B raised to B into RT raised to B. So taking these common terms together, we can write Kp is equal to concentration of C raised to C into D raised to D into RT raised to C plus D upon concentration of A raised to A into concentration of B raised to B into RT raised to A plus B, and hence we can write Kp is equal to Kc. Actually this is the Kc. We know Kc is equal to concentration of C raised to C into concentration of D raised to D upon concentration of A raised to A into concentration of B raised to B. So this is Kc. So Kc into RT raised to C plus D minus A plus B. C plus D minus A plus B. Now the difference between number of moles of gaseous products and number of moles of gaseous reactants, it is delta N. And so this C plus D minus A plus B, actually this is the number of moles of gaseous products, sum of number of moles of gaseous products minus sum of moles of gaseous reactants. This difference, it is delta N, and therefore Kp is equal to Kc into RT raised to delta N, and this is the relation between Kp and Kc. Now there are three important conditions. When delta N is 0, then Kp is equal to Kc. If this delta N is 0, this entire term, it will be 1, and therefore in that case Kp is equal to Kc. For example, consider this reaction. 2 moles of HI gas reversibly gives H2 gas plus I2 gas. Here 2 moles of products are formed from 2 moles of reactants, and therefore delta N is equal to 0, and for this reaction Kp is equal to Kc. Another condition is when delta N is greater than 0 or positive. In that case Kp must be greater than Kc. For example, 1 mole of gaseous phosphorus pentachloride reversibly gives, or on decomposition gives, 1 mole of phosphorus trichloride gas plus 1 mole of chlorine gas. Here 2 moles of products are formed from 1 mole of reactant, and therefore delta N is equal to 1 or positive, and hence for this reaction Kp is greater than Kc. And third important point is when delta N is less than 0 or negative, then Kp must be less than Kc. As an example, consider this reaction. 2 moles of SO2 gas, when mixed with 1 mole of oxygen gas, there is a formation of 2 moles of sulfur trioxide gas. It should be SO3 and not SO2. 2 moles of SO3 gas, it's a printing mistake. And here there is a formation of 2 moles of products from 3 moles of reactants, and therefore delta N, that is 2 minus 3, that is equal to minus 1. So here delta N is negative, and for this reaction Kp is less than Kc. So in this way we discussed about the relation between Kc and Kp, and the relation here is, this formula is important. Kp is equal to Kc into RT raised to delta N, where delta N is difference between number of moles of gaseous products and gaseous reactant. This delta N, it is considered for gas phase reactants and products only, and not other, that is liquid or solid phase.